Hello, I'm going to be talking about joint work with Christina Matake and Sam Staton. The setting is a programming language called PCF, which is typed lambda-calculus plus recursion. Categorically, a PCF category is a Cartesian closed category C with finite sums, equipped with a strong monad L, which we think of as adding an extra point to every object corresponding to the non-terminating computation, and that admits a family of fixed point operators. There is an initial PCF category P, whose objects and morphisms are given by the syntax of the language PCF. The question we're interested in becomes, can we find a PCF category C such that the induced functor from P to C is full, and C has the property that the home functor, the global sections functor, is faithful and preserves finite coproducts. So that means C is essentially a category of sets and functions in which every function between denotations of types is definable. The word sequential comes in because we think of PCF as being a sequential language, because every function has to use its arguments one at a time and can't recover from any non-termination errors. So there are no parallel constructs in PCF, and thus every function definable in PCF can be called a sequential function. We'll take that as a definition. A sequential model is a PCF category C with the properties just given. Ohan and Ricci showed how to build a sequential model by impredicatively collecting logical relations together. Now, logical relations were a tool developed to help characterize the definable morphisms in some given model. But if you build a model out of logical relations, you can do it in such a way that subsequently the logical relations you need to characterize definability are already featured in the definition of the model, and from there you prove that the model only contains definable things. Our contribution is to view the Ohan-Ricci construction as simply taking sheaves on a certain site. Another way that this gets simplified is that we don't have to use any domain theory in the traditional sense. We can do it in synthetic domain theory, which is sort of a way of looking at partial maps and fixed points in a topos. And I'll recap that briefly now. So the slogan for us may as well be a way of getting a PCF category from a topos with a distinguished monomorphism. Now, the point of the distinguished monomorphism is that in a topos, you ordinarily have a subobject classifier, but we also want a classifier for semi-decidable subobjects. Okay, so if I say that classical domain theory consists of studying the category of omega CPOs, that is, posets with all suprema of omega chains and maps on monotone functions that preserve the suprema of omega chains, then I can kind of complete omega CPO to a topos by taking a one-object full subcategory on the object omega bar, which is the successor of the first infinite ordinal, which is to say it's the natural numbers with their usual ordering together with a point at infinity above all of them. Now, the embedding from omega CPO into pre-sheaves on V is full, faithful. It preserves limits, coproducts, and exponentials. Okay, the distinguished monomorphism that we'll take is the inclusion of the top element of the two-element chain. Okay, so in this situation, the topos will admit a monad L, or L of delta, which classifies the partial maps into a given object. So Kleisli arrows from Y to X correspond to partial maps from Y to X, whose domain is semi-decidable, where semi-decidable means that it's a pullback of the distinguished monomorphism. So to get a PCF category, we have to define fixed point operators. We can't do this for general objects, but we can do it for objects which are complete in the following sense. So first we have to observe that we can represent the first infinite ordinal omega as a subobject of omega bar in our topos. And in fact, more generally in synthetic domain theory, we can define an omega and an omega bar using just the distinguished monomorphism and sufficient limits and colimits. So with omega and omega bar around, we say an object X is complete if the internal map from the omega bar sequences in X to the omega sequences in X is an isomorphism. This says that every sequence of points in X has a unique limit. Okay. What makes this synthetic is that every sequence is already a monotone sequence. Okay, and if we restrict to the subcategory of complete objects, then we get a PCF category because we can define fixed point operators. Going back to full definability in the Owen-Riehe construction, the first way we could get a sequential model would be to say work syntactically and define an equivalence relation on syntax and quotient P by it to get a sequential model. But we'd like to do it without mentioning the syntax or quotienting in that way. So the alternative approach is to collect up a set of guesses for the composite functor from P to C to set using the global sections functor on C. And then we use each of those guesses as an arity for logical relations. And you can, when I say logical relations, you should read base for pre-sheaves. This is essentially the idea behind the Owen-Riehe construction and the Jungian-Turin construction before. Okay, in our setting, we also want to have a subobject for synthetic domain theory. We want there to be enough complete objects for this subobject. And we also want to consider sum types, which are well known to cause problems for logical relations. And that's going to mean we have to use sheaves and not just pre-sheaves. Okay, so for our setting, a guess consists of a category C with the same objects as P and a faithful functor from C into the category of finite sets and partial maps, which is the Kleisli category for the error monad on finite sets. Okay, together with, for each object of C, a system of partial equivalence relations on the set F of tau. So the idea is that F of tau is a guess at the set of points of the type tau, and pi of tau is a guess for the set of functions from tau to a discrete finite set, partial functions to a discrete finite set, where the equivalence classes of the partial equivalence relation correspond to the fibers of such a function. Okay. Given a guess CF pi, construct a site ij as follows. The objects of I are an object tau equipped with a subset U of F of tau, which is the domain of some partial equivalence relation in pi of tau. The morphisms in I from sigma U to tau V are functions from U to V, including all the constant functions from U to V, and all the functions which arise from morphism in C from sigma to tau, whose restriction to U has image contained in V. Finally, the coverage is given by saying for each partial equivalence relation R in pi of tau, look at its partition classes. They give a cover of their union. Now we can build our site. Let SK be the site given by summing together the site V with the trivial coverage and each of the ij's for every possible guess CF pi with all terminal objects identified. We can extend the object delta, which was a functor on pre-sheaf on V, to a pre-sheaf on S by saying that delta S at tau U is the set of semi-decidable subsets of U. And the theorem is as follows. Delta S is a sheaf. The sheaf topos, together with this distinguished monomorphism, is a model of synthetic domain theory. And its subcategory of complete objects, which are also concrete sheaves, is a PCF category, and it is a sequential PCF category. Future work, we hope this will include looking at other computational effects, that is, other than just non-termination, and hopefully combining it with some recent work by Ohad Kamar, Shinya Katsumata, and Philip Saville on more general effects, not including recursion. Thank you very much for listening.